Okay, we are continuing here the second part. I got cut off the second part about the bivaritive normal. So we are talking about how we're taking all these slices and putting them close to each other. You should please refer to the first section of the bivaritive normal, part 1, but explained for kids like me. Okay, so what we're doing here is we're saying that we can see all these qualities that the books suggest in this model, in this cardboard paper that we're doing. First of all, each cardboard is like following a normal distribution. So you're given a certain x, y follows distribution. Each one has the same variance. They have each one a different expected value, because as the x goes higher, it means that as the height goes higher, the weight goes also a little bit above, so the y value goes higher. That is the second quality. The third quality is that the marginal distribution, meaning to say, this is not so obvious. You just have to trust the math geniuses that it's true. But it's intuitively true that each one has a marginal normal distribution, meaning to say, take together all these cardboards and squeeze them all together. Don't consider each y separately, each separate. Don't make the segregation of 6-footers and 5-10-footers. Take all the people together. That's like squeezing together all the x's. It's all the different x represents all the different heights. You squash them all together, you'll end up with a normal distribution. Weight. You only consider the y. The y is the weight. So y follows a normal distribution. You gotta know what is the variance of y and what is the general expected value of y, but there is a certain variance of y and a certain average of y. When you consider the whole population of the United States together, you're not interested now in differentiating between their heights. You just want to figure out the different weights. That means you're only considering the y. The y represents the weights. Y weights. So that is, it has a specific middle point. It means that that's the average, general average weight and a variance. Obviously, you can do the same thing with opposite. You can squeeze them together this way. It means you're squeezing them, instead of what should be close to your stomach and partially be away from your stomach, you squeeze them all together. So right now, you're not interested at all in the weights. You're just going to focus on the different heights, taking all the people with all different weights. You're not interested in differentiating. You're just considering the different heights. So again, there's a specific point that's the center, has an average height, and that follows a normal distribution. There's an expected value of x, because x is the height, and then there's a variance. And they're not the same. Could be the variance of the height is different, and the x, no connection whatsoever. So there's a few things that are, a few players in this game, basically, to sum it up. There's the expected x, means the average height. Then there's the variance of the height. Then there is the expected y, the average weight. Then there's the variance of the weight. And then is the subtle thing here that really, messes up stuff here, and that makes the complicated formulas in the book. That is the correlation, meaning to say, in the sense that, I'll listen to this one. When you put all these cardboards, and you want to draw a line on the table, that line will be exactly underneath the peak of each of these cardboards. That line will go on a certain slant, because as we say that the peak of the cardboards, the expected value of the weight gets higher as you go to taller people. So it goes on a slant. That is the linear relationship between the x and the y, and that is called the P, the rho as they call it in the textbooks. That, and without understanding exactly how the formula works out, there is a formula that tells you, if you know what is exactly the correlation, the p-value, then you could technically figure out describe this whole mountain, as I can call it. It's like a mountain that has interesting peaks, and it's in a specific way, and it's hard to exactly to imagine this as a 3D thing, but it's the best way that we can imagine it is the way I think is the best way is the way I described it here with the cardboards. Thank you for listening. I hope you enjoyed this.